move to the next speaker, so which is Kostas Skenderis, and he's going to tell us about holography and I guess a different picture of the resolution of the cosmological singularity.
Okay, thank you.
Welcome.
First, I'd like to thank the organizers for the opportunity to give this talk. I also to thank them in particular for giving me this perfect slot. And I hope to address the two previous talks, I think, also can serve as a perfect introduction to what I will discuss today, in particular, Roger's talk that we just heard. And I hope I will convince you that this new framework of holographic cosmology addresses precisely all the conceptual issues that Roger just discussed in the previous talk. So I will try to put some of this in the talk, but let me first start with kind of the bigger picture. So we're out here and we see some distribution of galaxies. And if we look further back in the past, we also see information coming from the CMB, from the recombination. But now if we're interested in addressing the questions, is there a combination of general relativity and quantum gravity? So one of the natural places to try to understand is what happens at the classical singularity. What happens over here? Can we describe the physics of the loss at the initial singularity? And we've heard from Alexei's talk earlier on that, okay, we could use inflation to describe the period over here. But of course, inflation doesn't explain really the initial singularity. But moreover, I think from the conceptual issue, I like to understand the question, can we address the connection? Is there something before the singularity? And we've seen in Roger's talk that he asked whether there is previous eons that come before the singularities. Or perhaps more ambitiously, can we formulate the laws of physics in that period where the notion of space and time, the way we perceive them today, did not make sense because we're just combining very quantum with general relativity. And if we can do this, if we can write a theory over here, is there something that we can see out there that has observational consequences of the observational signals from the way this initial singularity has been resolved? So these are the type of questions I would like to address. And en route, I will also try to address some of the conceptual issues that Roger posed in the previous talk. So what I will do today is I will start with giving you an introduction to what holographic cosmology is. I'm not assuming you're familiar with it. I'm also not assuming you're familiar with holographic dualities. So this first part is going to be mostly qualitative, try to put the main new ideas and the conceptual issues without many formulas. And then we'll move on towards, let's say, 2/3 of the talk to discuss a very simple holographic model where we can very concretely address the issue of the resolution of the initial singularity. So I would say this specific model does concretely address the question, can quantum gravity resolves, well, quantum gravity in a sense that I will discuss it here in holographic sense, addresses the resolution of the initial singularity, and the answer is yes. We will see it quite concretely, and then I would conclude. Do feel free to interrupt me. I know this is a short talk, but I think discussion is also important. Okay, so let me start from the beginning. So perhaps this is the most important talk, the most important slide of this talk. If there's anything you should get out of this talk, is this slide. So holographic cosmology is not just a specific model, it is a new framework for cosmology, and reformulates completely the way we view, in general, physical reality. So in usual models, like what Alexei told us in the morning, you start from a space-time perspective where you have some gravitational theory, possibly coupled to some matter, and you want to use maybe some perturbative expansion around some background to understand the physics. So to define the model, you give some bulk action, and then you use well-defined rules of perturbative quantization and to get predictions. So in holographic cosmology, we replace this with these two pieces of data. So instead of giving a four-dimensional theory, you give a three-dimensional quantum field theory. And I would like to emphasize that this is a quantum field theory on a fixed flat background. There is no gravity here. And on top of that, you give a dictionary, a so-called holographic dictionary, which relates the quantum field theory observables that you can directly compute in this quantum field theory to four-dimensional observables. And the four-dimensional observables I have in mind are not some theoretical abstract concepts, are the things we are observing, like power spectra or possibly non-Gaussianities further down the line. So this is a new framework, but this new framework already encompasses kind of previous works. For instance, it does encompass conventional inflation. In that context, this three-dimensional quantum field theory is a strongly coupled conformal field theory. But as with pretty much any new framework, allows to expand the parameter space of the things you can describe. So in particular, this new framework also allows for qualitatively new models, which describe a non-geometric very early universe, things that maybe you could describe from the bulk perspective as some quantum form, but in this case, in a very quantitative way. So these qualitatively new models, you cannot describe them as some Einstein gravity or some high derivative gravity coupled to matter, just because these are non-geometric. Even the notion of space-time and metric and geometry are not yet developed. So I could have given a talk discussing how holographic cosmology addresses issues of conventional inflation, but I'm not going to do this. I'm going to focus mostly on these new models for two reasons, these non-geometric models. And one reason is that I would like to start to get an idea of what it means to have the laws of physics if space or time do not make sense the way we present them today. I want to have a toy model where I can play with the ideas how to model such physics. And secondly, we will see that these models are compatible with current observations, and in addition, allow us to address this issue of the resolution of the initial singularity. Okay, so I think I pretty much just said this. So why doing holographic cosmology? So these models are fully consistent with quantum mechanics because they're based on a standard quantum field theory. They are consistent also with general relativity. General relativity emerges when the quantum field theory dynamics becomes strongly interacting in a very specific way. And moreover, these models are also well defined when traditional general relativity breaks down, including the initial singularity, which would be the focus of today's talk. And moreover, these models are compatible with data. So this is a comparison of the prediction of holographic cosmology with data from Planck 2015. Here just gave the angular spectrum from tensor perturbations, but they're exactly, in this papers we discuss also the polarization. So here I have the two curves. So first of all, the black dots are the Planck data. Then the red curve is holographic cosmology, and the dotted curve is lambda CDM. And you can see for high L's are pretty much on top of each other. This small part here, the insert here is the blow up for the small region, the small L region. And I'm going to come back to this later on. Of course, we shouldn't do physics with the eye, but let me give you also another slide that appeared, similar description that appears in one of Alexei's slides. So here in this plot, I have the residuals. So this green region is the Planck error. This black curve here, this is the difference between lambda CDM and holographic cosmology. The blue dots are Planck minus lambda CDM, and the red asterisk is Planck minus holographic cosmology. And you can see that the difference between the models cannot be distinguished with current data. And I will be a little bit more quantitative later on. Okay, so a few references. So there is very early work from about 20 years ago. We're trying to extend the so-called ADS-CFT correspondence to the context of cosmology. This came under the words the CFT correspondence. This was reinterpreted by Maldacena as the correspondence computing the wave function of the universe. And this is a picture that I will use later on. But what I will describe for the remaining of the talk is based on a general setup that started in papers with Paul McFadden about 10 years ago. And there's a lot of work where we developed many of the techniques, and we did the computations that I will describe later on. And the very last part about the resolution of the singularity is based on a very recent work, which is just published in PRL. This is a work done with a lattice group in Southampton and in Edinburgh, and is using lattice gauge theory methods in order to compute the quantum field theory observables at strong coupling, which is what you need in order to resolve the initial singularity. And I will describe this work a bit more later on. Okay. Now, to understand this talk, or to understand the conceptual underpinnings, we need some of the very basics of holography. And I would need this three different bullet points. First of all, gauge gravity duality is a weak, strong duality, which means that one description is strongly coupled, the other description is weakly coupled. So usually in most of the works done in holography, we want to understand strongly coupled quantum field theory, let's say confinement in QCD. And then we try to analyze this by looking at gravity in one dimension higher, which is perturbative. But holography, of course, goes both ways. So here we're going to use holography in the opposite direction. So we want to understand strongly coupled gravity. So this means that we should be using weakly coupled quantum field theory. So that's the first bullet point. The second bullet point is that there is the so-called UV-IR connection. So if you will be looking at the UV structure of the quantum field theory, then you have to look at the infrared structure of gravity, and vice versa. So again, in the existing literature, most of the work was done on this side. So you want to understand, let's say, anomalies or phenomenization in quantum field theory, and you can rephrase this in terms of infrared divergences on the gravitational side. So here we're going to use this the other way around. So in this talk, we want to understand the initial singularity. That's a UV issue in gravity. So this means that we should be looking in the infrared of the quantum field theory. And that's an important point. Actually, already here, I can go back to one of the last points that Roger made in his talk, that there is an asymmetry between the future and the past. And the asymmetry here is that there's also an asymmetry the way UV infinities and IR infinities are treated in quantum field theory. And that's how you see this very different behavior. The last point is about this holographic direction. So I will be using a three-dimensional quantum field theory. So what is the fourth direction that we perceive in everyday life? So this is associated with the energy scale with which we probe the quantum field theory. And this is going to be very important also in a minute. So these are the three main conceptual pillars.
Sorry, Kostas, you asked for interruptions, so
yes.
Let me interrupt.
Yes.
Roger was drawing a distinction between the past singularity and the future. When you talk about UV-IR, these are Euclidean concepts. So on the face of it, it seems to have nothing to do with time.
Okay, this just leads me to the next slide, time
Good.
And normalization group Flaw. So what is time in this framework? So in holographic cosmology, what you resolve holographically, what you generate holographically is time. So precisely the concepts that Roger is talking are related with the behavior of the quantum field theory under normalization group Flaw. And actually, in this case, cosmological evolution is inverse RG Flaw. So Roger had this very nice figure where you had the expansion of the gas and the behavior of the gravitational system. And you could see that the one looked the inverse of the other. So if you go, let's say if you start with the atoms in a room in a small corner and you let time flow, this is going to be uniform. And this was the exact opposite of the picture you see in gravity. That's precisely what this statement says. It says that the behavior in gravity is exactly the opposite to what you would expect on a normal quantum system with no gravity. Moreover, okay, now we know that renormalization group flaw in quantum field theory has monotonicity properties. So the monotonicity of renormalization group flaw is now linked to the R of time. And now that's another point that Roger made very strongly in the past, and he also mentioned in the talk, that the entropy that we see right now, it looks like the initial state had to be extremely low entropic. How is that possible? This looks very fine-tuning. But from the perspective of holography, this is completely natural, because we know that as we go from high energies to low energies, there is cross-graining, and there's fewer degrees of freedom in the IR. So there is it's not only it's natural, it's also universal. So the behavior in the infrared is universal. So the low entropic state is because as we go to the infrared, we have cross-graining of degrees of freedom.
So are you getting time out of a Wick rotation or analytic continuation from Euclidean time? How is time?
No, I'm not using any Wick rotation. This is the emergent direction, holographic direction.
So how do you get time out of a purely spatial model?
The time corresponds. Actually, let me see. Is this? It's in few slides. I have another diagram.
Sounds good.
So time, again, the holographic direction is the energy scale of the theory. And the energy scale of the theory translates under the holographic dictionary, becomes the time direction. So here we have the kind of conventional, the universe the way we see it. So it starts from a strongly coupled phase, and then it moves, gravity becomes weaker and weaker, because we know gravity is weak right now. So on this side of the diagram, so since gravity is weakly coupled here, we expect quantum field theory to be weakly coupled there. And as you go to the UV, then gravity becomes more and more strongly coupled here. That picture also qualitatively explains why we have dark energy. So dark energy, or the sitter-like phase, corresponds to the dual theory being a strongly coupled conformal field theory. And we know that the fixed points of quantum field theories are CFTs. So having a dark energy era is not only natural, I would say is a prediction of this holographic framework. Okay, so this is in pictures how it works. Now I'm going to have two slides, kind of what is the underlying mathematics. So what does holography compute? Okay, here I'm going to use this picture due to Maldacena. So this holographic picture, so it computes the wave function of the universe, where on the left-hand side, the argument, so if you view it here, suppose you have kind of an initial slice over here, and you give data there. Let's say the induced metric on the slice is one of the variables of the wave function. But that variable here gets reinterpreted in holography as a source that couples the gauge invariant operator. So if we're looking at a universal sector or gravity, then this phi would be the induced metric, and on that side would be the source that couples to the energy momentum tensor of the dual quantum field theory. Now this, so this is the partition function of the dual quantum field theory. And this partition function has the form I give over here. So it's given by the correlation functions of the gauge invariant operators of this theory multiplied with corresponding sources. So now So now this is the postulate. This is a holographic postulate. The wave function is equal to the quantum field theory. So if you want to do computations, you provide the quantum field theory, you compute the correlators, and if you want to compute cosmological observables, you square the wave function the way you do in quantum mechanics, and then you do the integral over the sources, and then this gives you the observables. Okay, now more concretely, if we want to move to discuss actual observables like power spectra, so in this case, the power spectrum is associated with the two-point function of the energy momentum tensor. I think this is probably the most technical slide of this talk. So in any quantum field theory, the two-point function has two pieces, has a piece, which is the transverse traceless piece of the correlator, and another piece, which is the scalar piece of the correlator. And these two pieces are precisely the pieces that you need in order to compute the power. The scalar power spectrum comes from this piece, put it in there, and then the tensor power spectrum comes from that piece, and you put it over there. So the way to do it, let's say, to compute these quantities is you give in a quantum field theory, and I will give you which one we're using in the next couple of slides. You compute this object, Planck it here, and get the prediction. Now, if you're interested in non-Gaussianities, then you need to consider higher point functions. So, for instance, the bispectral is 3-point functions, and so on. And there are very concrete formulas like this one that give all of these observables. All of this we have computed in the last 10 years. Okay, so now this is the general framework. Now, before I move to predictions, now this is the other slide I mentioned to Neil a few minutes ago. So I wanted to contrast also, of course, for a model of the very early universe to be credible, you should not only explain CMB, it should also be explain all other puzzles that we have associated with Horn-Big Bang cosmology. And here I'm just gonna very briefly explain how it resolves the horizon problem, and also try to make more clear what is the overall picture. So on the right, I have the usual picture of inflation, and on the left, I have, in a sense, the new version with holography. So let me very briefly remind you about the right. So if we would be just in Horn-Big Bang cosmology, we only have this part of the diagram. So this vertical axis is just time. We are up here. And with Horn-Big Bang cosmology, this would end into initial singularity, which is around there. And then the puzzle is, why do we see such uniform and isotropic temperature in CMB? Because if you go back, you use the light cone to go back, then the space-time would terminate the singularity before these 2 points have the chance to interact. Now in inflation, you say, okay, let's put another period before that, this exponential expansion, and then the light cones, then the past light cones over these 2 points would meet somewhere in the past, provided this is long enough, have enough if holdings. Of course, you still have an initial condition issue, and I think that's also mentioned both with Alexei and in Alexei's talk and in Roger's talk, because you still have this, the entire universe has to be originated by this part over here. And moreover, of course, inflation doesn't explain the initial singularity. This is still the space-time sort of ends in initial singularity, or you need new physics to explain what happens here. Now let's move to the right. So the top part of the diagram is exactly the same. So in the future, I would like to have a holographic model that holographically describes the physics here. I don't have this right now. I'm only gonna describe a model that describes this part of the diagram. So this is what they call here holographic phase. So here, this axis is the transitional time evolution. Here, this axis is renormalization group Flaw. Now, a subclass of models, if this model is a strongly coupled conformal field theory, then you will also have a semi-classical description, semi-classical gravitational description, where it's going to look exactly like we have over here. And now if you want to describe the power spectrum that we see today by looking at two distance points going back with past light cone, The way you compute those is by computing the 2-point function of the energy momentum tensor, one of them inserted here, and the other one inserted at this point. And this computation, you can do both when the quantum field theory is strongly coupled, and this is indicated by kind of this curve over here. This is a 2-point function in a geometric regime, and exactly reproduces what you get with inflation. But this picture here, most importantly, doesn't have, provided the infrared of the quantum field theory is well-defined, and I will give you arguments at the last part of the talk why it is well-defined. This picture is always well-defined. So the number of Efolniks over here translates into for how long in this normalization group Flaw you stay close to an infrared fixed point. Where here, the picture, even if you may not have semi-classical space-time at all, but you can still do the 2-point function computation of the quantum field theory, and you would still get exactly the right correlations that we observe with Planck in CMB. Okay. Good. So now, any questions on this? Okay, so now let me,
let me ask one, Kostas, again, since you're saying such interesting things. What about the question Roger was posing about the unlikeliness of the standard initial conditions? Does that?
Yeah, so in this case,
what?
Yeah, so I'll tell you, it does have something to say about that. Here it says, if I start at my UV fixed point over here, what is the chance that I deform the theory and this stays for a very long time close to the UV fixed point? Right. This is also a fine-tuning problem. But of course, in this case, I do not have to stay close to a UV fixed point where gravity is a strongly coupled UV fixed point where gravity is semi-classical, because I can do the computation also when the quantum effects are very strong. I do not need to have kind of a certain number of Efolniks to resolve the horizon problem. This is automatically resolved as long as the quantum field theory is finite in the infrared, which I will give you. I will give you a proof for a specific model in the remaining of this talk. Okay, so okay, now then the question is, what are the models? So here I will discuss a class of models, which are the ones that I fit into data, and I show you the fitting early on. So that we have this class of models which are based on a general coupling of gauge fields coupled to scalars and the fermions. So they have a 5⁴ interaction and a Yukawa coupling. They're all in the adjoint of SUN. And I think it is important to emphasize that this is not a CFT, because that theory contains a dimensionful coupling constant, the Yang-Mills coupling. The reason why we chose this class of models is because we know that this class of models appear in these are holographic models. You can set up the holographic dictionary. So now, starting from this class of models, then you can compute the 2-point function. And for this specific class of models, you can show in generality that the 2-point function takes the form I indicate over here, has a factor of n squared because we're doing a large n theory, and I will justify the large n in a few minutes. It has a factor of q cubed because the energy momentum tensor is dimension 3 in 3 dimensions. And in general is multiplied by general function of the dimensionless combination of the coupling constant with the momentum. So in this case, this is the appropriate coupling. So now if you're doing perturbation theory, this means you're considering scales Q such that this effective coupling is very small. So whether the theories are weakly coupled or strongly coupled depends on which scales you're looking at the theories. So if Q becomes very, very low, then G effective would become large, and then perturbation theory cannot be trusted. If on the other hand, Q is very large, then Q is very small, and then you can trust perturbation theory, and then you can ask are the scales that we see in CMB lie in this perturbative regime or not? And I will address this in a minute. So, if G effective is small, then the general form of the F is given over here. So this first term is the one loop approximation, and then these two terms are the two loop approximation. There is a log here because the theory has both UV and IR divergences, and these are going to become very, very important towards the end of the talk. So now we know the form of the two-point function even without doing any computation. So the computation just tells us what are these constants F0, F1, and F2. It just depends on the field content of the theory, how many vectors we have, how many scalars, and so on. So this means that for this class of theories, they're universal predictions about the form of the power spectrum. And this is it. So this is the form of the power spectrum. And you should contrast this with what we saw earlier on from Alexei, where for the scalar power spectrum, this was kind of this form of here, had a kind of a polynomial or monomial behavior with some spectral index NS. So here, instead of having this behavior, you have a sort of logarithmic behavior. So the same is true for the tensor power spectra. And there is also the non-Gaussianities are also very special. And I give here the description, but I don't have time to explain. But suppose, for instance, there's no local non-Gaussianity. Suppose tomorrow non-Gaussianity is measured, and they found that there is a local non-Gaussianity of, let's say, FNL2. This is going to rule out completely immediately these models. Or suppose they measure the collateral non-Gaussianity of a collateral shape, and the answer is 5. So these specific models, all of them universally have an FNL, which is a pure number. So all dependence on the field content, coupling constants, and all that, it cancels out when you do the computation, and you get this 5/36. Okay, so so currently we have bounds for the tensors, and we have measured the scalars. So then one can ask, do the data prefer this power spectrum or that one? And this is the plot I gave you the very early, the beginning of the talk. And here are kind of a little bit more quantitative results. So the feature data, it did shows that this effective coupling is indeed small. So this is, in a sense, a posteriori, you justify the assumption you made with the model, namely you can use perturbation theory. This is justified for all scales we see at the CMP except the very low multiples. So when L is less than 30, roughly in the region where you have cosmic variance, the model becomes non-predictive, so that you cannot trust the perturbative expansion. So you need a different way to compute the predictions there. If you do goodness of fit in the regime where both lambda CDM and holographic cosmology are good description, then you find that chi-square is about the same. So they're both within one sigma. So the data do not prefer one or the other, which we saw also visually. And secondly, the fit to data also makes a model selection. For instance, one finds that gauge theory coupled to fermions only is not a good model for the very early universe. You need an SUN gauge theory coupled to a number of non-minimal scalars with a 5^4 interaction. So this is the class of models preferred by the data. Okay, so now if you want to...
Kostas, you've had half an hour, so if you could try and finish
Oh, okay. Okay, so good. So let me skip this. So I want to at least give you a glimpse of this resolution of the initial singularity. So in this last part, I'm going to discuss a very simple model, which is we drop completely the gauge fields and we just consider a single scalar. So this model has only 2 parameters. So these are SUN, every scalar is an SUN matrix. So one parameter is n, and this is a non-minimal scalar, meaning the energy momentum tensor contains an improvement term with a new parameter. So I have 2 parameters, n and psi. So n is actually fixed when you compare with observations by the amplitude of primordial perturbations. So it's something like 10 to the 4. So large n limit is extremely good. So the parametric psi is related with a number of tensors. So this is the ratios of scalars to tensors. So this model is not perturbative in the entire regime. The effective coupling becomes large or around 260. So if you want to compute the full predictions of this very simple model, then you need to do something non-perturbatively. But in the regime where this model is well defined, when L is greater than 260, you can compare the predictions of that model with lambda CDM. And this model is about a bit more of 2 sigma better than lambda CDM. So that's, this was a big surprise to me that this very simple model in the perturbative regime can fit the high L data so well. So we need to address the low L regime, but the low L regime is also where the singularity resolution comes in. So these models that I have been discussing are supernormalizable quantum field theories. And because they're supernormalizable, they have severe infrared divergences. But 40 years ago, this gentleman here conjectured that these theories are non-perturbatively infrared finite, where the Young-Mills coupling effectively plays the role of the infrared regulator. So since time evolution is an inverse RG flaw, this resolution here, so we have an infrared singularity the same way that we have a bulk initial singularity. But this model contains an intrinsic mechanism that resolves this initial singularity. So this was a conjecture based on a simple model. So I wanted to test whether this mechanism is at work for the model I described here. And to do that, you need to use a computational method that allows to compute strongly coupled quantum field theory. And the only currently available such method is really lattice quantum field theory. So we embarked on this journey. I think it's now more than 2, 3 years working on this, to analyze this problem using lattice quantum field theory. And there are a lot of things to be done. So here I'm just gonna flash through some of the results about the second point. So if you're in the continuum, it's very easy to understand what is a massless quantum field theory. You say it's a theory that has no mass term. But on a lattice, this is much harder to quantify. So you need to adjust the bare mass into your action and fine tune its value so that the theory becomes massless in the continuum limit. So this bare mass you can compute in perturbation theory. It's infrared divergent up to 2 loops, but that's not an issue. You can deal with this with standard normalization. But it's also, more importantly, infrared divergent starting from 2 loops. So unless these infrared infinities are absent non-perturbatively, the theory doesn't make sense, and the massless theory doesn't exist. And this model I have been describing, it's just not a viable model. It's theoretically kind of nonsense. So, so we computed this massless point non-perturbative using a method called analyzing the behavior of the theory as you change the bare mass from positive to negative. So it has to go through 0. And this is captured but from the way the correlation functions behave as you go from one regime to the other. So it kind of has a theta function behavior. Okay, so now we computed this. So we can explicitly extract this finite infrared value. But then the question is, does this have a well-defined limit when you remove the infrared regulator? If you're on the lattice, the finite volume of the theory acts as an infrared regulator. So we had to distinguish between a model where the coupling constant of the theory acts as an infrared regulator. This is a model which is infrared finite in the continuum limit, and a model where the lattice size is the infrared regulator, and then there is infrared divergence in the continuum limit. So then if the second is true, then the model wouldn't make sense. And to test between the two, we computed the so-called Bayesian evidence, and this is indicated in that diagram. So I think in this diagram, there are 2 things. This is a busy diagram, but just focus on 2 parts. So the circles and the color. So if the circles are within this pink zone, then you would say the data do not support model 1 or model 2. If the circles would be in the yellow zone, then you would say, if it is here, you would say there is some strong evidence for model 1 over model 2. And if it would be here, you would say there is a strong evidence for model 2 rather than model 1. And if it's up here, it is decisive evidence for model 1 over model 2. In terms of kind of high energy language, 5 sigma evidence would be somewhere around here. And you can see here, so I mean, this is overwhelming. I mean, this is undisputable evidence that this model is infrared finite. And this is an explicit mechanism that resolves the infrared singularity, and then by holography, the initial singularity. Now, of course, one could ask, can you actually now see observational evidence of that? And for that, one needs to compute, finish, in a sense, my to-do list, find the energy momentum, tensor compute the 2-point functions, and compare it with data. And we're not there yet, but we have computed kind of an easier quantity. And you can see this is a coupling constant. So this is a non-perturbative region. That's 1 loop prediction, 2 loop prediction. So you can see the lattice does allow us to go to the non-perturbative regime. So hopefully in the near future, we'll be able to see whether this non-perturbative resolution of the initial singularity is actually visible also in the data that we have from Planck. Okay, so I'm sorry I have been over time. Let me just quickly summarize. I think I try to convince you that holography offers a unified framework that includes both conventional inflationary models in terms of some strongly coupled quantum field theory, but also includes qualitatively new models where the very early universe is non-geometric. And in the context of holography, the resolution of the initial singularity maps to the infrared finiteness of the quantum field theory. And in order to access this region, we really need to use lattice method. And this is something which is ongoing. And hopefully we'll be able to address the questions where there are observational signatures of the singularity resolution in the near future. Thank you very much for the attention, and apologies.
No problem. Thank you, Kostas, for a beautiful talk. Are there any questions?
Yeah, may I ask a question?
Is that Sergey?
No, Ignatius.
Ignatius. Okay, go ahead, Ignatius, and then Sergey, and then Sebastian.
In the model of 5 to the 4 that you looked at the end, I noticed you don't have a coupling in front of the quartic coupling in front of 5 to the 4. Is why you choose to be 1?
Yeah, so no, I didn't choose it to be a 1. In 3 dimensions, specifically in 3 dimensions, you can scale it away. So there is a scaling argument that can set that coupling to 1.
It's a mass parameter. There is a mass parameter, or it's
it's not a mass parameter. So all terms, so if I go back to this model here, so there is a dimensional parameter, which is G Yang-Mills. And then the couplings here are all, so these terms have the same dimension. So it's dimensionless because I moved out the coupling constant.
Oh,
so if I can scale it back if you want instead to go to the
U. Okay. Thank you. Yeah. And another short question. What is the holographic dual of this model in terms of gravity? Is it pure gravity, or it has matter?
No, that has other stuff as well. It's not just pure gravity, because for every gauge invariant operator that you cannot come up with this theory, there should be an object in the bulk. So if I write, let's say, 5 to the 4 is an operator. So this means there should be a scalar field in the bulk with a specific mass related to the dimension and so on. So here I focus on kind of the gravitational part, because this is the part where we have actual current data.
But this scalar part has to do with the inflaton, for instance, or in some regime, classical, semi-classical regime?
No, I think the inflaton, the more, let's say, if you want kind of an analog of the inflaton, would be the dual of the entire action.
Okay.
That would be the analog of the dual, not just 5 to the 4, but the entire Lagrangian.
Okay, Sergey? You had a question?
Yes, I also want to ask about the tensor to scalar ratio. Is it an arbitrary parameter in your model?
So in this case, it's related to this parameter psi. So at this point, it is an arbitrary parameter. So if let's say you find for tensors, R to be 0.003, that would say that psi is close to 1/8 up to this factor of 0.003. So once tensors are found, hopefully they will be found in the next 5 to 10 years, this would completely pin down all parameters of that model, because we already know n from the amplitude of the perturbations, and we know psi because of the tensors, and then everything else they have to come automatically. They're going to be no adjustable parameter anymore.
And another question, what is about bound solutions in holographic cosmology? Is it possible or not?
Say it again.
What is about bound solutions?
Oh, bound solutions.
Yes.
I mean, everything in the block does have an image in the boundary. And now specific objects, so if you tell me a specific bound solution, like, a star, okay, then I can try to understand what this would imply in terms of correlation functions of the dual quantum field theory. We're not yet at the point to be able to, you give me a solution and I immediately tell you what it is, but I know what I have to study in order to be able to answer your question.
Okay, thank you.
Okay, let's have Sebastian.
Yeah, I'd like to ask a very generic question. So if I understand correctly, you define the non-geometric pre-Big Bang phase just as the dual of the QFT. So what selects the QFT? Like how generic or specific is the choice of the QFT?
So the quantum field theories I selected are the ones in a generic perturbative quantum field theory, because it starts with canonical kinetic terms. What is very special is that all fields are massless, and that's very important. So if I make the fields massive, then I will not have the correct power spectrum. But then having the masses be absent also means that they still have a special property. This is called generalized conformal structure. It is the property I briefly mentioned when I address Ignatius' question. So all the terms in the actions, they scale the same way if you assign them four-dimensional dimensions. And this has the implication that for all of these cases, the two-point functions have this generic form I give over here. So from my perspective, it is the more general kind of perturbative quantum field theory. It has no mass terms, and it has this generalized conformal structure. And we know that these theories admit a holographic dictionary. So that's what characterizes.
Okay, thank you.
Mikhail, I think you're next.
Let me ask the following question, Kostas. So the model you start with on the boundary side, it very much similar to the model that Klebanov and Polyakov conjectured to be due to higher spin theory and higher spin fields. So anyway, there are some higher spin operators due to the operators on the boundary side. So is that a kind of a version of higher spin theory that what you're considering for?
Yeah, so I mean, this is the main difference between these models and the ones in kind of Klebanov Polyakov. The other ones are vector models, where this one are kind of tensor models. So the phi field is a matrix rather than a vector. And the coupling is, the 5 to the 4 coupling is a single trace, where in the ON models, this is a double trace. That does have implications. Now, when we go to the perturbative regime, then it is true that there would be high spin currents, which are perturbatively broken by the interactions.
Yeah.
And I think that's important things to analyze to see whether there are observational consequences of those. I mean, that also relates to the question that Ignatius asked me in the beginning. Are there any other things, or is it just gravity? So it's not just gravity, it's gravity coupled to many other things. You can easily incorporate well, easily. You can incorporate the standard model the way we understand it by adjusting what is this dual quantum field theory. But you would also generically, so in this non-geometric regime, you would include high spin currents, and then we need to understand what are the implications of those in observations. So that's another thing in my list to do. It is a very interesting question.
Okay, thank you. So it looks like that there is a chance that this is spontaneously broken phase of higher spin theory in the end of the day, one way or another.
Well, very close to the perturbative point, I think, because also there you expect, since this is a very quantum phase, so if this will have kind of a string theory description, you would also expect the string kind of states to be relevant. And then part of the string states would be related to the high spins as well.
Okay, thank you very much.
Okay, maybe a last question from Alexei.
Okay, thank you, Kostas, for this very interesting talk. But just because I prefer to think not in terms of for the space, speaking about time, speaking about the history of our universe in the past, according to your model, what was before inflation or instead of inflation?
Yeah, so this is so this model, this strongly coupled models replaces inflation. So you do not need, so if this model here is weakly coupled quantum field theory, you don't have inflation. And you need, so the heating, so at this point in the current development of the model, we have the model, and then we have instant reheating at tau equals 0.
But did you have always expansion or contraction with some bounds or an isotropic phase in the past?
Well, the very end of that phase in these non-geometric models looks more like power law inflation, the very end part.
I see, thank you.
But I should say, in a sense, I don't have yet a kind of a smooth reheating phase where I exit from that phase smoothly to this region. I only have kind of a perturbative model. I only have, in a sense, the very first baby steps. I mean, this is, I would say, in terms of the big framework, this is the thing which is most urgent to understand if you want how to extend that phase in a better way. Than currently, kind of instant reheating, it's, I mean, we do not see, in a sense, anything, because the data at high Ls, which would be affected also by that phase, seem to be fit very well. So that seems to suggest that there is something analog with what happens with the zeta variable, that kind of the reheating phase doesn't affect this specific observable. But nevertheless, it is a very important problem to have a very concrete phase that tells you how to smoothly go from here to there.
It's the same problem for all inflationary models, a graceful exit from inflation.
Okay, maybe Chaeyu Chen, since if you have a quick question, we could fit you in.
Oh, yes, thank you for the nice talk. So here you only focus on the initial singularity in cosmology, but we know that the black hole singularity is another issue in generativity. And also there's a fact that we can map the interior black hole as kind of an isotropic cosmology. So my question is what is the obstacles, or can we simply apply this argument to resolve black hole singularities?
Yes, I think there is a similar story. Actually, holography started from black holes. And so the idea started as an answer to the question, why the black hole entropy scales like the area? And then the answer was because the actual degrees of freedom are living in quantum field theory, will not gravity in one dimension less. And then the entropy of that system scales like the volume, which is an area in one dimension higher. Okay, so then you can ask, okay, how does holography address the issue of the singularity inside black holes? And there you can use, again, the similar tools of ADS-CFT. there it's a somewhat different resolution. It's not exactly the same resolution. There, what the dictionary says that the insight should be non-singular, but should be like a fuzz that extends all the way to the horizon. Some people call this the fuzz proposal of for black holes, and it's completely non-singular, removes the horizon, and introduces this non-trivial kind of fuzz, which captures into the fact that you have non-trivial expectation values or Gaussian variant operators. So if you want to read about this, I wrote a physics report about 10, 12 years ago.
Okay.
Thank you.
Thank you, everybody. And thank you all the speakers and all the people who asked questions, and look forward to the next session.